Welcome back to the next video, everybody. Today, we're going to continue our foray into the basic review and discussion of the Archimedean representation theory of GL2. So we're going to be looking at GL2 of R. And today's video will be a little bit about some of the main examples that we'll need to keep in mind. So we'll let G equals GL2 of R, the main group of focus. We'll let mu1 and mu2 denote two characters of R star. We'll let H equals H1 of mu1, mu2 be the Hilbert space of functions F from G to C, such that F evaluated at the matrix A1x0 A2 times G is just the square root of absolute value of A1 over A2 times mu1 of A1, mu2 of A2 times F of G. And this should hold for all A1x0 A2 in the Borel subgroup B of upper triangular matrices of G. Okay, and we also want to make sure that the integral over K, where K is the maximal compact subgroup of orthogonal matrices of f of k squared dk is less than infinity. So this is a typical kind of like L2 condition on the functions. And we'll just denote this quantity here by a kind of double bar of f squared. In fact, technically speaking, we actually want the set of such continuous f, and then we want to take the closure of this set with respect to this norm here. But, let's just keep the main ideas in focus here. So the right regular action of G on functions f in H of mu1, mu2, what I mean by that is the action that sends f to fg for a fixed g in big G, where fg is defined to be the function fg of h is f of hg for all h and g. That defines an admissible representation of G. Admissibility was defined last video. We denote this representation pi of mu1, mu2, and it's called the representation of G induced from the character mu1, mu2, technically of B, but you can drop that. Most people wouldn't say that, given the context was clear. Okay, now remember, every one of these representations also has a GK module perspective. So what's the corresponding GK module here? We'll call it V sub k. And what it is it consists of finite linear combinations of smooth functions, which we'll call phi sub k. And they're defined by phi sub k of G equals mu1 of A1, mu2 of A2 times e to the negative ik theta, where G has what we call an Iwasawa decomposition into an upper triangular matrix times a rotation. So in other words, G looks like, one of our typical A1x0 A2s from above, from our Borel subgroup, times R of theta. And what is R of theta here? It's the rotation matrix, cosine theta, negative sine theta, cosine theta, which is in K. Okay, so we have kind of upper triangular times, something from our maximal compact subgroup. And there's a technical compatibility condition we also want to make sure of. We want to make sure that mu1, mu2 of -1 is e to the negative ik pi. And this has to do with the elements in plus or minus the identity, which live in B intersect K. I don't want to get into it, but technically it's part of the decomposition if we want to be thorough. Okay, so why are we looking at this example? Well, first of all, there's a couple of facts to be aware of. First of all, it's pretty easy to check when these are irreducible in some sense. You can check that pi of mu1, mu2 is irreducible if and only if mu1 times mu2 inverse of x isn't equal to x to the n times the sine function of x for n and n. But more importantly, the following theorem holds: every irreducible admissible representation pi of G, and those are exactly the representations we're looking at that we're after for the Langlands conjectures, is equivalent to pi of mu1, mu2 for some mu1 and mu2, or an irreducible subrepresentation thereof. So some irreducible subrepresentation of this. So in some sense, these representations induced by characters govern all of the admissible irreducible representations on GL2 of R. So they're quite important, as you might imagine then. Okay, so how about those irreducible subrepresentations? Well, let's suppose mu1, mu2 inverse of x is equal to x to the n sine of x for some n and n. And so by this fact up here, we have reducibility. Well, then H of mu1, mu2 contains exactly one invariant subspace. And so the restriction then of pi of mu1, mu2 to this subspace is, this is then going to be an irreducible representation. And we call it the irreducible discrete series representation of lowest weight p plus 1. Okay, so even when we're considering the situation where this representation induced by two characters, or induced by the character mu1, mu2, is reducible, we sort of have a handle on what the invariant subspaces are. We have a handle on what kind of the irreducible subrepresentations are. They're just these discrete series representations. Okay, one last little slide. I'm also going to define central character for you. This is a term I've been using for a couple of videos. For any irreducible admissible representation pi of G, Schur's lemma type argument implies that there's a character of R star, which we'll denote by omega sub pi. And this is called the central character of pi. And what does the central character do? It governs how the representation behaves on scalar matrices, essentially. So it has the property that pi of the matrix R0, 0, R is just omega sub pi of R times I, where I is the identity matrix. And this should hold for all R and R star. Okay, and so that's what the central character is. I didn't give a lot of references or proofs, but I just in general think you should read Knapp's local Langlands correspondence, the Archimedean case, for far more information and details on the above. It's a great survey. It may not provide details for all the proofs for all of these things, but it will contain further references which do. So this is a great place to start. Okay, so next video, we'll start looking at the p-adic representation theory of GL2. So I'll see you then, and thanks for watching.